poklikao. Pa sad upalite pa ćemo onda gasiti kad bude trebalo gasiti. Sad možemo malo samo zrak pustiti kao čisti. Hi. Okay, so let's start with this lecture today. The first part of the lecture is devoted to the ultrasound equipment as well, but this time we are more going to speak about the treatment and therapy with ultrasound. So the principles are the same, but there will be some new terms to learn when we speak about treatment and therapy, because obviously the power that is used is much larger than the power that's needed for ultrasound imaging, and therefore the effects will be non-linear, so to say, though everything having to do with ultrasound is actually described by some relations that are non-linear. And after that we will just make an introduction to the laboratory, to one of these demo laboratory exercises, so that you get the framework, let's say, of the safety of of or for the electromedical devices. So we will talk only about the electrical aspect, not about the aspect dealing with any kind of radiation, ionizing or non-ionizing. It is actually, all these standards are actually an example of very detailed work and thinking of engineers, though there are so many rules that sometimes it looks a little bit boring, but they have to be obeyed, because without obeying them you cannot bring the devices to the market. And then we will see also one specialized device that is used for testing that. So since two of your colleagues declared that they cannot come because they went back to Slavonia and they're like following everything from there, we have the streaming, and the demonstration is going to be done in such a way that we form two groups. So one group will be with me here, and we will try to make it possible for them to see at least something. And the other one is going to be in the back, so that we can talk here, and that they who are listening to me, let's say, and to some questions that I will ask you, that they can hear this part, and the other one I will also ask to be relatively quiet, so that it's easier to understand. And then we will change the equipment, and Jai is going to present the second part, and I'm going to go with the safety analyzers into the corner, so that we can make both things. Your exam, in case you decided to enter this first one, so-called continuous learning, will be on Monday at 2 o'clock. So the time was changed because of students, because I know that the students like to sleep a little bit longer. And that's also the case with my assistants, so that you will meet with Jaya at 2 o'clock. And I believe, since you are a small group, that it will be possible to finish the evaluation of the exams also tomorrow. On Monday. And I will then make two groups. One group will be Tuesday early afternoon, lunchtime or something like that. The other one will be on Wednesday, also like mid-time and so on. So I will allow you to choose which group to attend for the oral examination. So it will be like 4 places on Tuesday and 4 places on Wednesday. And then we will meet, you will be sitting probably here or in one of the other labs far away, and I will be pending from one to the other. So since the exam is so very close to the end of the semester, I will allow you to send me questions by email until Sunday noon, okay? So if you send me any question that you want to discuss or something like that to get my answer, you can do it until Sunday noon. Then after that, it's like before the elections, 24 hours of silence, okay? Fine. So let's start with this one here. So in the first part of the ultrasound, we were mainly speaking about the diagnostic applications of the medical ultrasound, and today we will speak a little bit about these two first treatment and therapy possibilities that are used for ultrasound in medicine. About the deep tissue heating, actually it's, so to say, a little bit lower application of this, let's say, part of the application, so I will not be talking into details. So firstly, the name lithotripsy comes from the fact that in this medical procedure you use some kind of shock waves, and actually these shock waves can also be used with laser to destroy something, and these things that you are actually destroying are hardened masses. We usually speak about some kind of stones that are generated in the mainly urinary tract of the human body. These stones may be different chemical composition, but most of them may be destroyed by ultrasound. So when we speak about lithotripsy, then there are several possibilities of using ultrasound, also, as I said, laser. So we will be talking about these two particular one. One is percutaneous ultrasonic lithotripsy, where we will see that we use a probe to enter into the body and to do the job. And in the other one, actually, there is no penetration of a device into the body, but the ultrasound is directed in a very complicated, so to say, setting, and therefore it's also expensive, and therefore it's of course not used that often. But this one, we may say, that is actually practically non-invasive. So invasive is only the ultrasound. There is no entering of the body. So the first one, the percutaneous ultrasonic lithotripsy, or more medical saying of the same term, is percutaneous nephrolithotomy. Tomy is always when you take something out, vasotomy and so on. Tomy, take out. So as I said, this is a little bit more medical kind of vocabulary. So what you have to have is a device. This device obviously generates the ultrasound waves. Very often you have some kind of a liquid and a pump that is pumping some liquid in and then sucking it out in order to take some of the particles out. And then if you have a look at the procedure itself, then you may recognize this very large mass here. So you come into the contact with this stone. You then apply then the ultrasound, which is then transmitted to this stone. As you can see on this image here, you get smaller particles. So they are either sucked out, they may be taken out partially by some mechanical device, hand or grabbing device, or some of the smaller ones are just released during the urination, so that goes very easily out of the body. So as you can see on this image, which is more schematic, you will have this one contact part that comes in contact with the stone. So as you can see, it's called nephroscope because it's scoping. It's something that is looking into the device, and then of course you have some kind of a lead that is enabling that you enter to the place where you would like to actually make this destroying of the channel. There are a lot of different kind of probes that are used, so that it's not so easy to make a systematization. The destroying of the stones in urinary tract may be done by ultrasound, but also may be done pneumatically. That means by some system that is based also on mechanical vibrations, but it's not the vibrations are not generated in the same way as with the ultrasound. Anyway, the device, as you can see, is relatively small. remember when we have a look at the next device that I'm going to present, the extracorporeal device, how large that one and how large that one, how large it is and how complicated it is, which actually means that this is a device that may be used much more broadly. It doesn't need so much assistance. It's cheaper, so it's more available to the patients. So the energy that is transmitted is actually vibration, not heat in this case, and not shock waves. The first devices were, so to say, working only on a single frequency, but during the years of application of lithotripsy, people have learned that actually the different frequencies of using or for destroying of these stones may be useful for different kind of the stones. So therefore in today's there are so-called dual ultrasonic lithotripsers, which will then use two frequencies that are actually called the high and the low frequency. But when we go and have a look at these frequencies, then you can actually see that the frequencies are not that far away. So it's from 20.4 kilohertz to 22.2 kilohertz. So it's obviously in lower in lower part of the ultrasonic spectrum. And the probe, of course, it's handheld, and the part that comes into the contact with the stone is actually this large and long metallic stick, which is usually produced by titanium or titanium alloys. There are some of the dimensions that are interesting to see. As you can see, the dimensions are relatively large when you speak about the transducer itself. It's about 4 centimeters. And the probe itself is about 4 millimeters. So this device that is penetrating through the skin is 4 millimeters, which is not so bad actually. So to say that the hole is actually relatively small. And then you see for this particular device, the output power is approximately 100 watt. So it's not too much. If you remember, we had the electrosurgical devices where the output power was declared up to 1 kilowatt. So this is much smaller energy. So this is a more technical, so to say, description of the lithotripsy probe. So the acoustic part, so to say, is actually here. So these are the piezoelectric elements where you again actually come with some kind of power supply. So this part is then actually vibrating. The vibrations are then transferred through this rod, and they come into the contact with the stones. And then the electrical part, there is some kind of a motor that is enabling suction, so that all these particles are then sucked into this tube and actually taken out of the body. So again, longitudinal vibration, that means transversal movement of the ultrasonic wave. The other thing, it's metallic, so in this part, in the transmission, there is practically no loss. So the quantity of the energy that is released to the sides of this pipe or of this rod is very, very little. Therefore, they may be so effective. And the contact is necessary so that you can really destroy it, because otherwise, as you remember, there is the exponential decay in the power when the wave, ultrasound wave, travels through the soft tissue. So if you were a few centimeters away, it would be necessary to introduce too much power, so the soft tissue between the stone and the probe would be actually destroyed in one or the other way, because the entry point would have too high energy for, so to say, for surviving. And then this is the other possibility which I wanted to mention. It's called extracorporeal shockwave lithotripsy. So as I said, it's also used for breaking of the stones, but as you can see, the source here is coming from far away, let's say, from out of the body, and then when the kidney stones are destroyed, then they will also be released through the urinary tract. Now, can you see the difference in the device? This is a complete, let's say, system that is actually existing of this applicatory part. So this applicatory part will be that part that comes into the contact with the human body. So you may imagine that there is a patient lying here, and with this part here you actually touch somewhere in his, let's say, in his back at the height of the kidneys that have to be, so to say, cleaned out. And the action must be also followed. So usually there are two screens. One screen is usually, there are two screens, and you may use fluoroscopic, that means X-ray, live X-ray, or you may use ultrasound to see whether you have targeted the stones or whether you have missed them, so to say. And of course also before that there may be for sure some images from before, from medical imaging, so to say, so that the medical doctor, medical staff knows what and when and how to apply. And the other ones are probably having to do with ECG, with monitoring, perhaps oxygen and so on and so on. Actually, it says here in this list, but I will not now go through that. Of course, this part may be adjusted in the position. So as you can see on this slide here, it may be also rotated so that the ultrasound wave may target the stones. So this part here is plastic, of course, and though it seems that you will be lying on this part when they put you on this table here, it still needs some kind of the feeling between the skin and this ultrasonic head, so that in most cases it's also used, the gel is also used here, so that you have the feeling that there is no air in between. So this is, let's say, the principle of operation. What you are actually doing to the stones is, of course, this applicatory part. As you can see in this device here, the head is filled with water. The conditions for or the characteristics of this water may also be very, very specific. So you have like ordinary water. In ordinary water that we drink from the system, from like at home and so on, there are some small bubbles of air. So therefore they don't like that. And then the water they put usually in these transducers is distillated and then also demineralized. That means that there are no particles in there. So it's, so to say, very pure, 100% pure water. 100% perhaps not, but 99.9 or something like that. So here you have to have the beam that is going to target this kidney stone on this image here, and then in order to actually see in real time, you are using one X-ray tube that's coming from the bottom of the patient, and here the for this X-ray visualization there is the image intensifier. So I don't know whether those of you who are listening to the biological systems, signals and systems, whether you have heard that with X-ray. So it's a actually transducer which is actually transferring the X-rays to light, and then the light then with the photomultiplicator into electrical signals. It's quite a complicated actually device. Perhaps even I have it one that's not working anymore, so we perhaps can find it in the lab there. So anyway, I think that's all that we have to know about this here picture, and then again a little bit more technical schematics. This water field casting, that's this part here, and then out of plastics made acoustic lens so that you can direct the ultrasound, and the so to say generator of the vibrations and so on is put here at the bottom of such a device. Today, in many cases, they are using actually more than one shock wave, so to say. So in this case, you can see that there are two transducers, and in the first, let's say, step of the whole procedure, you are using one, and in the second step you're using the other transducers. These two transducers are operating at very close but different frequencies, so they found out that it is more efficient in actually smashing these stones. So let's say the energy requirements for the waves are dependent on different kind of the stones, and then of course different parts of the body are actually producing the different kind of composition of these stones. So the how long do you have to apply the ultrasound in order to be efficient? It's actually the duration of this application is dependent on the energy level and on the frequency. Usually the lower the frequency, the higher energy may be transmitted. That's one of the laws. And then when we look into the whole story, the advantages of such procedures are that they are non-invasive. This part here is obvious. There is no general anesthesia since you are not penetrating the body like it should be. Painless, but it's not painless, but the level of pain is different than the level of pain you have in surgery or something like that. It's actually treatment time, so it's a short treatment time. It's relatively convenient because actually the patient may just walk in and so on and so on. And it's considered to be safe, no infections and so on, because you are not penetrating the patient's skin and so on. So for such devices, and that's just one example, these kind of devices are very different from different kind of producers. But anyway, just to get the idea, so the focal distance is 135 millimeters. That means that somebody calculated that the average depth of the kidney in the human body is around this distance. It's always better from the point of view of using the same device with different people. So some people may be fat and something like that, so the distance to the stone is larger. So if you need, therefore you need some larger depth. And then if you have somebody who is skinny, you can adjust that you move those devices that are actually within the whole, let's say, head of that probe, that large probe, to higher depth, so that you can always reach the focusing. So as you can see, the dimension of, let's say, the cross area is around 7.5 to 2 centimeters, 7.5 millimeters, so it's relatively small. You can generate pressures up to 1,200 bars. So this shock, of course, they cannot last too long, because if they last too long, then you would get the heating effects and so on and so on. So they have to be limited into a shorter, let's say, bursts. Then the localization of the stones you make in situ during the surgery by by ultrasound or by fluoroscopy. The shape of those lenses is ellipsoidal. That means that you can shape them to go deeper than if you had just a circle, and the patient coupling is, so to say, dry. That means that you don't have to make any kind of penetration. It's dry in that way that there is no necessity to enter the patient's body. So something that came as a new methodology relatively lately is the so-called high-intensity focused ultrasound. The Americans, they like to make abbreviations for everything. So let me see, what's the destruction mechanism here. So you heat or you ablate the tissue. So that's another, let's say, principle. The difference here actually is that you focus this high intensity ultrasound, so you really have to find some smaller point, and then it needn't be, there is no need to have a contact with the probe. So this is actually meant for destroying soft tissue. So today it's relatively popular for destroying of malignant tumors like prostate. So that's one of the, let's say, easily reachable tumors for this technology. So the destruction may be through heating or through mechanical vibrations and so on. So both is actually allowed. Then also the high intensity focus ultrasound may be used also for massage. That means for increasing the blood flow or the flow of the lymph in certain areas. In this case, of course, it is not destructive. So the power that is transmitted must be much, much lower, of course. And of course, also when applied, then you usually apply it with some imaging technology. So in the case of ultrasound, it's popular to use it with MRI, which actually has to do with that the transducer itself and the lens are made of non-magnetic materials, so everything can be made out of plastic and so on. So that's the possibility to use it also together in the same space where the MRI machine is actually positioned. So again, schematic transducer. This transducer will also be composed as an array. So if you not remember, in the diagnostic we said that we have like the planar waves and some kind of the focused waves. So here you also play with this focusing, and the part that is focused is relatively small. I know that I put the dimensions, perhaps it's on the other slide. In this case, the tumor is within the liver, and the good, so to say, characteristic of such a technology is that you actually destroy the tumor, so to say, point by point. So you go around and into the depth of the tumor, and then you do it so in repetitive sending of these ultrasound waves into the body, so that it may also last a little bit, so to say, longer. It's, let's say, similar to the cobalt knife, which is used, let's say, for tumors in the head. The difference is that you have in these devices, you have, it's called also radiological knife. You have, let's say, about 60 sources of radioactive cobalt. So you have individual rays, and then you use these individual rays in such a way that you focus the radiation on different kind of shapes. So each ray, when it passes through the skull and the skin and the parts of the brain where there is no tumor, the energy there is very, very small. But out of 60 of those sources, you may find relatively large volumes that are then irradiated in such a way that they destroy the tumor. The fantastic thing in our body is actually that with this methodology and with this X-ray or radioactive methodology, you destroy the tumors that are relatively large, like diameter 2 or 3 centimeters, and the body takes care to take all the particles that are left, because these are now dead cells, you know, so they have to be taken out and replaced, and that happens after the treatment. And with, let's say, both of these treatments, you don't feel that, so it doesn't cause any pain or something like that. So that's actually fantastic. So, it's here. You see here also the frequencies that are used for diagnostic ultrasound in these cases are relatively low, 250. This is like 250 kilohertz to 2 megahertz. In the diagnostics today, we go to 20 megahertz for the ultrasound. That means also that the the dimensions of the targets is relatively large. So we don't use this at, let's say, 10 or 20 or even 5 megahertz, because the dimensions of the tumor have to be relatively large. So two small tumors cannot be treated by this this way. So what are we expecting to happen with the tissue? The target temperature of the tissue that we want to destroy is between 65 and 85 degrees. What actually happens with the bjelančevina, with the proteins, yeah, thank you, sorry. With the proteins is that they are destroyed at temperatures higher than 60 degrees. So this limit depends on the size and so on and so on. Anyway, they are trying to design the whole process in such a way that the temperatures are not too large, because in case of too large temperatures, boiling, you might generate also steam, which would then be also destroying some tissue around, because it would want to get out of the body. So the sonication is the expression that is actually used for this kind of the destroying and of the energy actually that is transmitted. It also goes into several waves of the whole procedures. And then there is a nice formula which is talking about the transfer of the energy. So in this procedure they call it cumulative equivalent minutes. So of course it's an integral, so time is multiplying something. What is something? This something here is a constant that is experimentally actually reached. It is, as it says, 0.5 for temperatures over 43 and 0.25 for 37 to 43 degrees. And where does the 43 come? The 43 comes here, and the other temperature comes here. So that there is a calculation for each tumor and so on, how to actually grab it and so on. What we have also in in ultrasound is the term of cavitation. Because of these vibrations, what may actually happen is that these small bubbles of actually which are different in the composition from the other tissue, that they actually are either explode or implode. Which means, if you have a look at this image here, in ultrasound we have these transversal waves, okay? So with such, let's say, imagine that this is a bubble of a liquid, or a bubble of let's say air, of some kind of a gas. So when you have the compression phase, such a bubble will become smaller, and then you have the relaxation phase, it becomes larger, and then with further increasing of the energy, that means of the amplitude of these waves, it may stay stable. But if the amplitude is larger, so you can see it here because the waves look a little bit larger, then it may happen that you actually get this either implosion or that we call actually cavitation. That means that this bubble it's like the pressure within the bubble is so now actually small that it breaks and it actually sucks in something that is around that then is being destroyed. So this is actually the story about this all kinds of, let's say, destroying of the tissue that is so to say used in different kind of treatments. And with that I will close. Anyway, you can find a lot of the references here beyond, so if you have any interest to follow some of these images to get some additional explanation, then you can use that as so to say as the guide. Okay, fine. Any questions? No? Okay, so the next let's say lecture will be now on the safety. So with that safety we have also the safety analyzer, which we will demonstrate. So for that reason I sent this also email with the link, okay, for streaming. So you should have got it. So I don't mind, and actually I ask you to see that you can connect and how and what you see, because I will go now to bring the analyzer, and then at a certain moment I will put it here somewhere, and then we have to make a decision where is it the better position, because there is more light on the right hand side and less light but the screen here, so perhaps I will make the projection of the slides on the smaller screen and the projection or using the light from here. So we have to look at that, and also to have a look when I switch on the light and off the light, what we see and so on. So please try. I don't know whether it works on each and every mobile phone, but our colleague Jure Petrovic, who is in charge of that, he says that it should be working everywhere, because it's like only a YouTube channel and it's open. So I hope it will work well. So I will paste it here so that I can actually transmit this to the small computer. You may now open some of the windows and the door. Steve shall I? Dobra, nie ma szuma. Okay. I'll see you in a few minutes. snažno. Može? Okay. Nije to tako teško, ali jednostavno ne spomenuje čovjek. On? Znači, cilj nam je da ništa ne padne, jel? Mora da biti malo. Može? Ide? Evo, tu smo već s kotačima, sad mi samo gurajte. Dobro. Ajde sad neko gledajte samo, znači, recimo, šta sad vidite, odnosno jel vidite nešto na ovome? Evo dođi mi na da, bio bih sretni na ovo, da je malo više detalja, ali morat ćemo s tim nešto možda prepoznati. Ok, shvatili smo još jednu stvar. Ok, evo recimo to će ovak biti onda u nekom trenutku za demonstraciju. Ja samo malo da pogledam kako se ovaj drugi vidi. Dobro, ok, thanks. Dobro. Znači, sad ćemo da vidim samo ovo ovdje. Sad ćemo kao uvodno proći ove tu slajdove, da vidimo, tako je, ok. Pa onda u nekom trenutku kad već dođemo u vezi sa samom prezentacijom do nečeg što je za pokazati zapravo ovdje na ovim recimo uređajima, onda ću vam to pokazati, a onda ćemo hands on napraviti kad završim sa prezentacijom. Ne pozvat ćemo Džaju da on dođe i tako, jel? No, znači, u današnje vrijeme bez tehnologije zapravo se ne može više bilo šta napraviti zapravo u medicini. I ja sam imao jedan slajd s jednim navodom od one veteranske administracije u Americi. Nekako Amerikanci su ratovali svugdje i slično, bilo je to doduše iz vremena još post-vijetnamskog rata, ali su oni već tada rekli da 86 svih dijagnostika i terapija i tretmana se donosi na temelju, znači, određene dijagnostičke vrijednosti ili, dakle, vrijednosti koja se upotrebljava u terapiji. Znači, u 86% toga sudjeluje neka tehnologija. Vjerojatno da danas u svijetu je toga i više, samo što to nitko više nakon tog nije na taj način dakle, objavio. Jel? No, reci. Oh, sorry, why didn't you say anything? So I'm speaking in Croatian. Sorry, I just forgot. No, you were missing 2 times in a row, you know, so I a little bit forgot on you, but yeah. Okay, so sorry. So actually, what I said is that there is a data from veteran administration from USA, where they say that 86% of all the diagnostic, treatment and therapeutic, let's say, values are derived today from instrumentational technology. And that was in the time between the Vietnam War and no other war that happened in between. Today it's perhaps even more difficult. So the main issue that we have as engineers to deal with is actually to develop safe devices. So we are here in line with the medical doctors, where they say, firstly, no harm. This is actually the reason why all this development in biomedical engineering, but also in other fields that are present in medicine, like pharmacology, they last long. And that's why also when they develop the vaccines, it takes it takes people, times people to let's say prove that something is safe for application on human. So let's say the dangers for the patients are not coming primarily from medical devices. So here is some kind of things that are more, let's say, dangerous for the patients. Mostly these things have to do with some kind of blood, other penetration into the body, infections and so on, or in changing the blood groups in patients. And then also the hazardous chemicals. So in this sense here, primarily the medicines, the pills, so to say, and then also anesthetics, waking out of the actually of the sleep after the anesthesia, which is very, very important, and it takes a lot of time. And finally the medical gases, because where you have oxygen and some anesthetics, it's possible to develop some explosions and so on. And biologically, the so-called hospital infections are very much present. These are bacteria that are resistant to any antibiotics, so that again, when we speak about the biomedical engineering part of the intervention here, is actually in which way would it be possible to destroy these bacteria, because obviously with antibiotics it doesn't work. So one of the ideas is that some of the liquids that are used in the hospital, here I don't think like blood or infusion, but let's say sewage water and so on, are processed through high voltage pulses that then kill the bacteria in such a way that they destroy the membrane, because bacteria is very simple, so it's one cell beans, and that's one of the ideas. Also, everything that comes like liquid water before usage, they would like to pass it through such a system. So that's it. And then here the fourth tab is the one where most of the, let's say, electrical, electronic devices are coming in with a very, very large variety. So from the point of view of the security, what we will be talking today will be based on the physiological effects of the electricity. And so to say, the other thing we will just touch, and then as a demonstration we will have a look at a part of the testing of the biomedical devices. So in order to achieve some kind of effects, we have to make the human body a part of the circuit. So we were already speaking about pacemakers, we were speaking about defibrillator cardioverters, we were speaking about electrosurgical devices. In each of these cases, a part of the tissue, a part of an organ, or the organ as a whole is included into the electrical circuit. And so we saw all the, let's say, positive effects of electrical current, the IT or strength duration curve, which is actually enabling some kind of a modeling of electrical stimulation, which is then important for devices like pacemakers, where you have repetitive stimulation in order to keep the person alive. So this is actually an example of real stimulation. When we actually speak about heating of tissue, in this case we practically can say that electrosurgical devices are transforming electrical energy into heat, and in this way they actually enable this removal of some parts of the tissue, tumor or something like that. And burns are actually unwanted, but may be used also in electrosurgery to stop bleeding. So when we speak about the intended use of electrical currents for stimulation, then the intended use is usually moving of some muscles and so on. When I was discussing pacemakers, I already told you that the reason for using rectangular pulses is the simplicity of their generation. For more powerful pulses, like those ones used in defibrillation, we use those bipolar or biphasic pulses because it was experimentally proven that the energy that is transferred to the body by such pulses is less than with the damped sine wave, and therefore in these cases we take more willingness to make this power entering the body lower and so on. So I will comment just this one here, this graph here, which is actually showing in a way different IT or strength duration curves that are experimentally obtained from one person. Of course, when they make this kind of experiments, they usually test several people. So when we speak about the IT curve or strength duration curve, then we have, of course, the stimulation duration and the threshold or the amplitude of the current. What you can see here is that firstly, if this energy, so to say, of the stimulating pulses is low, that you actually do not have any feeling of the current flowing through your body. But then there is this lowest curve, which is actually the perception. That means now I start feeling that something is happening, and then if you increase it a little bit, then you get some motor response. You can move some parts of the body, let's say. Then when you increase it relatively a lot, then you first get the pain. But then, you know, when something is painful, it may be a little bit painful, and then it may be also the level of tolerance. The tolerance, that means you can't bear it anymore. So usually the patients these are usually healthy people who are volunteers for such kind of testing. They have some kind of a red button, and then when they cannot tolerate anymore, they then press it, and the whole experiment is over. Anyway, this seems to be very close, but you have to see that it's a logarithmic scale. So therefore, in this logarithmic scale, like from this value to, let's say, this value here, it's 5 times larger amount. Okay. So when we are thinking about the stimulation, then we have to think about this as the effects that we are wanting to obtain. That's usually this motor or perception in some replacement of some stimuli and so on. So for different amplitudes of the, or sorry, it's not amplitude, it's the effective value. The effects that are obtained are given in this image here. So as you can see here again, we have some kind of currents from 1 to 10 milliamps where you have the threshold, and then this is the so-called let go current. The let go current is, so to say, borderline value. So when you want to test, let's say, a device, and let's just take the case that you do not have any instrument, no multimeter, nothing else. What you have to do is actually to knock on the device. Why? Because if you get a larger current through your muscles, then they will actually shrink, and if you touch something like a wire in such a way and it's online, you will not be able to leave it. So you have a let go current. That means this is the current where you are like holding something that's online, that's hot, but you can still leave it. You can still remove your hand, okay? And then of course you have the other consequences: respiratory paralysis, fatigue, pain, ventricular fibrillation, and here we go to the let's say end stage of the tissue. That means that these values will cause them very soon some kind of final destroying of either myocardial muscle or skin or something like that. So these kind of let's say values may be also transmitted into another kind of a graph, where you have actually the graph that is representing the current voltage values. This is also actually non-linear, but the effect of a particular current at different voltages may not be the same, so that it has to be taken into consideration. And you can see I noted here fibrillation and convulsion, and these are the expected values of the impedance at particular currents or voltages. So you will be able to read that later, so that we go further on. So here we have again one of the graphs that is showing actually the current, time or strength duration curve for different wave shapes, and also the same for the charge. So the strength duration curve was already commented, so I won't go through that again. But the other one is perhaps interesting, because on the x axis you have the frequency of the signal. So the curves here are always so to say showing the sensitivity for a particular current or current density. So what we can see here is that the frequencies around 50 Hertz, that's here, designate that the tissue, the human tissue, that means heart, nerves, muscles, are most sensitive to frequencies that are around 50 Hertz. So 50 Hertz, which is our mains, is actually among the most dangerous frequencies, because if you go to the higher frequencies, you need much higher current to cause the same kind of sensation or the same kind of damage to the tissue. But of course, nobody is going to change the mains now to higher or to lower frequency, because the infrastructure is too large, so that we can just forget it. We just have to be aware of this here. And therefore, in order to make the medical devices, the devices generally, and then medical devices safer, there are some threshold sets. So for the alternating current, we may see that safety extra low voltages. this is the aberration, are considered those that are below 50 volt at the frequencies 50 or 60 hertz. And then medical safety voltages are then only 25 volt. For DC current, so if you remember the strength duration curve, then for very long pulses you come into that asymptotic part of the curve, which is then asymptotic to the Rao basis. In that case, that means that for DC currents, the human body, the cells are not actually sensitive, and therefore these voltages here at 0 hertz are 120 volts or 60 volt for medical devices. So, as we said, the electrical shock, when it comes especially in the relaxation phase of the heart contraction, may cause very easily fibrillation of the heart. So whenever there is some current introduced close to human heart, then it should be synchronized with the ECG, so that the first edge of such a pulse is not coming at the time of that part of the T wave. So for the reasons of analysis of the different currents to different parts of the body, there are different kind of segments as a model of human body developed. And in these, let's say, developments, what is usually, so to say, considered is actually the term that is said to be a micro shock or a micro or a macro shock. In English it sounds very, very similar. So when we have a micro shock, that means that a person has really connected himself or herself into the circuit in such a way that the current flows through the heart. And this is, let's say, a relatively rare case. The micro shocks are those that may happen due to the leakage currents about which we are going to talk today, because when you have a catheter in the heart, then the heart itself is very, very sensitive to very low values of the current. When the electrode or the conductive part of a catheter through which there is a possibility for a leakage current, that in this case it may be turned into fibrillation. So that the micro shocks, though it looks micro, it's something very small, because of this situation of the definition that micro shock is caused from a source that is closing the loop or the electrical circuit directly through the heart. It is, so to say, much more possible than the macro shock, which may be just an accident in a kitchen or something like that. So the main protection is against the micro shocks and the macro and micro shocks is actually protective grounding. So the protective grounding, it is, let's say, the third wire that we have in the mains, and it is locally connected to the earth, so that all the currents that are flowing to the protective ground actually cannot cause voltages high enough to make any damage to the heart in terms of macro or micro shocks. It's the protective ground is, so to say, keeping the voltage that appears on metallic parts of the device is very, very low. So some of the limitations here are given in numbers like half a volt or 40 millivolts. And then many of the devices that are working in clinical environments have also some so-called circuits for the detection of leakage currents. So actually what's happening here is that these devices are actually measuring the currents in the ground wire and in the neutral wire, and based on the difference in the voltage, in case the voltage is higher than prescribed by a standard, they will cut the circuit out. When we speak about the other part of the dangers from the mains, it is the falling out of the power. So what has to be restored 10 seconds after the power failure is the lighting, the alarms, and the equipment in the intensive care. So that's something that the supply system in a hospital has to provide. So the protection of all the equipment in medical environments is such that the first failure that occurs should not make any damage to any person or to equipment or something like that. So that's why it is called the safe equipment during the first failure. So it has to be done in such a way that the person is not endangered, but the first protection against that is actually the grounding of the the grounding of the equipment. So the leakage currents are those that are usually flowing through bad isolation. These are the currents that we do not design when we design a device. So as we could see, the leakage currents are actually more dangerous if they are at, let's say, the middle frequencies or frequencies from a few tenths of hertz to a few hundredths of hertz. So they normally occur on medical devices that are powered by the mains, because you may have the capacitive or the inductive actually character of these currents that are then flowing also through the body. So these are the pathways for different kinds of these currents. So as I said, the small device that you can see here is actually devoted to measuring all the possible situations and all to see what kind of currents may be leaking through different parts of the device. Because if you remember, I told you that in many medical devices you have somewhere the isolation circuit. So this isolation circuit means that one part of the device and the other part of the device may have different leakage currents, because they actually get their power source from different sources. So here in these three graphs, you can actually see which are the possible situations. So apart from all the measurements that have to be done, what I would like you to remember that one of the main things that has to be taken care of is actually the voltage difference or the leakage current between neutral and ground. That is usually that part where we detect that there is that a part of isolation of a part of a circuit is not anymore correct. So these are some of these spots that can be, so to say, closed. You can see here the one coming from the secondary of the transformer, which is closing, and this is through the housing of the device, and there is another leakage current that is flowing to the ground. So these leakage currents that are leading from the housing of the device through the body to the ground, or from a part of the equipment through the patient to the ground, these are those that are, let's say, considered to be more dangerous. For these ones that are leaking through metallic parts to the protective ground, that value may be higher because it cannot cause so much danger. So as you see here, 100 and 100 microamps are these two cases that I said, and for the earth leakage current, the third one, it may be 0.5 milliamp. So here is, let's say, some of the examples of this pathway, so I will let you read that. The safety of medical devices is actually regulated through some laws, through some regulations, and through the standards. So the new laws are actually regulating this kind of devices in such a way that they refer to standards, to the compliance with the standards in order to prove the safety of the devices. So that is a very constructive, so to say, step, because since it is referred to the standards, you always know when the standard will change. When you bring a new standard this year, it will be effective in 2 years. So in 2 years, all the companies producing medical devices have time to adopt in order to see how they are going to be able to comply with all these standards. So the main standard for the medical safety is or actually the series is marked by this number 6601. So these devices are now presented here. So I will first speak about the new one that we are going to use for some of these tests. Today, as you can see, if you compare the yellow one with the old one that is in the white box, they are obviously smaller because more of these tests are automatically produced and just directed through a few buttons and LCD display. The other one here has practically the same functionalities. It's not anymore in function because this device that we see down there was actually intended for real calibration and testing of the medical equipment and reporting, so that you have here a small printer. Unfortunately, this small printer is not working anymore. And the second reason why we are not using it is that the standard 6601-1 has changed. So actually the values that are memorized in the some kind of EPROM in this device here are not the right ones. So we might use it on the exercises because for a particular training how to deal with that device, it doesn't matter whether the value is 50 or 100 microamps, but still we succeeded to buy this new one so that we can have a up-to-date device. So all these devices that are coming from the International Electrotechnical Commission, if they have an extension -1 and then dash something else, then they are general. That means they apply to all medical equipment. And then if you want to have a standard that is applicable only for defibrillators, that's the other one, the other test that we are going to have, then there will be a -2 and then again some number that is going to mark actually a particular product. So these are all those, let's say, things that are being tested here, so that you can see that this is actually a very small part from the general standard that are being tested. And so this is actually what we are going to do, general analyzer and defibrillator analyzer. So the general standard is grouping, so to say, the characteristics for 4 classes of instruments, and they are actually listed here. So you can see group 1 with enhanced risk is all those devices that are invasive, either with radiation or with the power of ultrasound or by the electrical current that is used for cutting tissue or something like that. The group 2 is active implants, so you already know what are active implants. The group 3 is normal risk. Normal risk, it is ECGs, EEGs, all these devices that are mainly diagnostic, where you do not push any power through the patient. And then finally household, that means blood pressure meter that you or your grandmother has at home and so on. So as you can see, there are some rules that have to be obeyed, but there is no further testing. Oops, I was talking too long. There is no further testing for all these house appliances. The other ones have to be tested, and there are now the requirements for each of these groups of the devices. And finally, this is one of the things that also have to be understood with all the products, being biomedical engineering products like medical devices, or let's say vaccines. What you can see here, there is no 100% safety. Therefore, at least my opinion, as let's say a scientist who is following the literature that deals with medicine, technology, and so on, you know, nobody can sign that there won't be any casualties from vaccination. But you know now that it's already probably at least 1 month that they are having mass vaccinations in England and in some other countries. I am not even talking about China and Russia, because European Union is not believing that they have effective vaccines. But it's obviously that in this whole period there had not been any remarkable casualties, and therefore I believe that it would really be good for the population that they get these vaccines, and that all this it's difficult to say nonsense, but it's a nonsense for all of us living, especially for you kids, because I go home and then I work most of the evenings, or I read, or I look at the TV, but you want to go out and have some fun and so on, and you have to sit at home. So that's really not fair towards you. So I really hope that you will be released from the leash very, very soon. This was also this last slide. And as I said, it's important that you remember that for the safety, for higher safety, you have to, so to say, pay a higher price. Okay? So now the 6 of you divide into 2 groups. One will come with me here, the other one will be with Dominic with the defibrillators, and then we will change after we show something to you so that some of you can touch and so on. So I don't mind, you can find your own preferences for the groups. We can perhaps make let's make 5 minutes break so that we change a little bit the air, so we can open the door and so on, and then we will. Jeste vi svi prijavili ispit sad i mislite svi izaći? Ne? Mi smo završili smo, pa možeš ti polako doći. Ajde, može ba. Dobro, ok. Tak samo da znam da računam, onda znači ja vam preporučujem vi koji mislite da ste se bolje spremili, da se onda javite za utorak za ispit, ono ko još malo treba za spremat se onda nekom zbog se. To nije puno. Imate još neki drugi ispit koji je a? Šta imate utorak? Aha, dobro.
I usmeni stoje isti dan.
Isti dan, pa koliko vas slušaju?
Ili u srijedu.
Kako?
Ili u srijedu. Biće par grupa.
Da, a gledaj, mislim, mislim, ja mogu biti, što se mene tiče, ja mogu biti fleksibilni. Znači, ako bi se nešto poklopilo ili slično, ja vas mogu kasniti. I'm talking in duration, because I already asked you, since you are leaving, which day you want to have your exams. So, Ruben is going to come on Wednesday, so I allow him to make the first choice since he's the first one to leave.
Can you repeat? Sorry. I mean, you're talking about what you are talking about? Sorry, about what you are talking about?
I'm talking about the exam, okay?
Okay, the exam.
So I just said that I let you choose the day of the exam first, because you are leaving. You said you are leaving on the 20. You are leaving back to Spain, aren't you?
Yeah.
Yes, so it's better that we make the exam here than per distance and so on. Okay?
Okay.
Ja mislim da nam ovo zapravo neće trebat, jer tu neću ništa prikazivati. Pogledam kak se vidi ovo, sad sam uključio još ovo druga. Molim? Mislim, tamo su sigurno štekeri, ne znam da li ima koji na ovo negdje. Kada se možda primao šome kutove, kada samo da vidimo malo kak se sjene bacaju. Vidim sad kad dođete tu.
Uzima koja sekunda?
Ja, nema veze. Evo recimo ono što oni mogu vidjeti, ako imaju na velikom ekranu, onda možda nešto mogu vidjeti. To je to, ček samo da vidim ako ovo neću, nešto se događa. Ako ovo nećem tu, se vidi šta. Dobro, nije. Gdje se će tu?
Smeta sad. Ima nekih par sekundi.
Ja nije dobro, morao biti bliže. Ok. Dobro, stoji tu. Aha, znači si sigurno 5 put potaknuo, dobro. Dakle, ajmo vidjeti, ako ti dođeš tu si, možeš vidjeti, dobro je još kad ja odem ovdje. Dobro, znači, hajde.
Samo koliko će se na ekranima vidjeti?
Ko? Molim? A nešto gledaj, nešto će moći vidjeti, pa ja ću probati nešto reći slično. Ajmo sad, koja još dvojica hoće doći ovamo? A moramo početi, ne? Okay. The other three has to come in the second round, so it's more or less not very difficult choice, okay? Da si sad gledaš šta se vidi, gdje mogu stajati, sorry.
Svuda tuda oko.
Ja, mislim da bi kolega možda...
A možete po jedan.
Meni je malo predaleko, ne, za gledat tamo.
Ajde, po jedan, one person.
Ćemo staviti ovako pa da vidimo.
Koga?
Mobitel. nama na stolicu tamo.
Aha, mislite da mobitel da gledamo paralelno?
Pa mislim, rekli ste da...
Ne, da vidim sad kam kolege kad dođu tu bliže.
Aha.
Ok, ajde dođite sad, stanite tu. I vi stanite tu. Dobro, 1, 2, gdje je treći? Aha,
sad će treći.
Delay i tako dalje. So, ovak, vi budete tu, a ja ću onda ovo malo probati okretati i slično. Sad više ne možemo za ove kolege koji gledaju od doma previše u detalje gledati šta se događa i slično. Okay. Dobro, znači ovdje samo sam htio reći, metno sam još isto ovu listu standarda koji su prisutni u tom svijetu. To nisu svi i to su samo od IEC-a. Znači recimo Amerika ima svoje standarde, ali puno njih su zapravo potpuno kompatibilni. U nekim stvarima je Amerika malo stroža, u nekima možda Evropa, ali uglavnom onda kad idete na to da zadovoljite sve standarde. I kao što sam rekao, ne, ovi tu 1, pa 1, 2, 3, 4, 6, 8 su generalni vrede za sve. Ovi tu kad se tu gledaju, ne, onda recimo ono što smo radili za ovaj standard 2, povlaka 2 je High Frequency Surgical Equipment. Pa će tu biti obrađeno ono što smo mi tamo pričali, bit će dane granice ono maksimalne, minimalne i slično. Ne? Evo tu su defibrilatori, tu su elektrokardiografi i tako dalje, za svaki pojedini uređaj postoji. Znači nekako pravilo po kojem se on mora još posebno ispitati. Često se dogodi da u tom posebnom standardu onda piše aha, ovi dijelovi općeg standarda ne vrijede, jer su besmisleni za to. Ćeš gledat sad za nekakvi monitor, da li recimo zrači ili level zračenja neionizirajućeg zračenja i tako ne? To bi bilo to. Sad, znači ovo je tu uređaj, svo ovo ispitivanje, bez obzira da li se radi s ovim uređajem ili s ovim ovdje, su u principu relativno dosadni, jer se mjere zapravo naponi, struje i otpori, ali u beskrajno mnogo zapravo kombinacija. Jel? Međutim, kad se sad kreće sa tim samim ispitivanjem, onda zapravo naravno se mora krenuti od toga da se negdje uključimo u struju. To ćemo sad prvo zapravo napraviti. Znači imamo produžni kabel tu negdje. Tako i sad gdje imamo, ja mislim da imamo tu dole struju, jel? Evo ga. Dobro. I kako se zove sada, možemo početi gledati šta će se tu zapravo dogoditi. Kad ja sad tu, na primjer, uključim ovo ovdje, on će se automatski uključiti. Dobro. I sad on prvo šta radi je to da napravi jedan self-test. To sad traje neko vrijeme. I sad šta on kaže? Evo, na primjer, ovo nije sad bilo ciljano, jel? Jer nisam ništa, kad sam došao tu nisam gledao gdje je faza, gdje je nula. On sad, na primjer, javlja fault detection. Znači, polarity reversed. Čega?
Dakle, sa ovih mjera, za mjerenje, sendera za mjerenje.
Ne, napajanja. Znači, ono što je sad bitna stvar, da on sebi sam ustanovi, on kod tog self-testa zapravo gleda između kojih dviju žica koje su, ajmo, dio aktivnog kruga, znači ono što bi mi rekli plus i minus, koja od tih je na manjem naponu prema zaštitnom uzemljenju. Ne? I sad šta moram sad napraviti? Moramo krenuti. Sad odem dole. I kad to napravim, sad će se on ponovno uključiti, sad će on ponovno napraviti self-test. Pa sad moramo malo čekati. Evo.
Zašto to ima veze?
Molim?
Zašto to ima veze kod ovog uređaja, na primjer?
Pa, zato što mora znati šta mu je referenca. Ne? Znači, dakle, cijelo ovo testiranje, dakle, kad on treba napraviti nekakvi izvještaj da je nešto u redu i slično, ne, onda on mora znati šta je zapravo, koje struje teku prema zaštitnom uzemljenju, a koje teku prema znači protective earth, odnosno zaštitnom uzemljenju, koje je prema nuli. Ok, sada, u čemu je problem, ne? Ovo je uređaj koji se želi napraviti tako da bude što je moguće jednostavnije. Okay? A da bi on mogao biti što je moguće jednostavniji, onda je njemu jednostavnije reći ti okreni šteker, nego da ja moram sad tu nešto mijenjati, odnosno da moram unutra imati switch koji će mi reći aha sad ovo mjerim prema žici koja je u zaštitno uzemljenje, koja je 0, dakle 0 i 220 su izmjenjivi, jer kad se ide na bilo koji obično transformator i slično, tam ti je svejedno plus minus. S druge strane je neki ispravljač uglavnom i to je uglavnom ta stvar. Dobro. Tak, sad bih ja samo molio moj šalabahter tamo ovu bijelu knjižicu da znam kojim redoslijedom ćemo ići. Hvala. Znači, u principu on dakle, kroz to testiranje on zapravo vodi, ne? Tu je kao na početku, ne, vidite, dakle, tamo, dakle, prva stvar koju kaže je, tu kaže koje sve veličine se spominju, znači, u smislu, evo, mreže, pa onda zaštitno uzemljenje, pa onda struja koja teče kroz sam uređaj, odnosno u uređaj, to je napajanje ove kante tu, znači onda koliko je curenje prema zaštitnom uzemljenju, koliko je curenje prema housingu, prema dakle, kućištu, znači koliko je iz aktivnih dijelova curenje i onda pojedino curenje između dviju točaka, odnosno impedancija, odnosno otpor između pojedinih točaka. Sad kaže koji je intentive use, dakle tu sad opisuje da mjeri prema samome ovome, dakle, standardu i slično. Sad je tu hrpa upozorenja šta smiješ raditi, šta ne smiješ raditi i tak dalje, to nećemo komentirati jer su to zapravo relativno normalne stvari. Samo isto morate još jednu stvar isto, da tako kažem, zapamtiti, ne? Da koliko god iz vlastitog iskustva znate da ima dobrih tehničara, dobrih majstora, naravno i dobrih inženjera, ali uvijek morate znati da, pogotovo kad se radi o nekakvom sustavu gdje se ide u neku masovnu proizvodnju i slično, uvijek se ide gledati posao koji može raditi, što bi se reklo čistačica, radi čistačica, jel? Jer ona ne može raditi nešto što radi tajnica koja tipka ili ne znam, neki inženjer koji projektira ili neki prohoć koji, da tako kažem, ne znam, predaje ili tako nešto. Znači, i ovdje nastojite zapravo napraviti nešto što će praktički neko sa ono što je bilo 3 razreda srednje škole, nekakve električarske moći zapravo napraviti, jer je to nekakva, da tako kažem, rutina i slično. Pa radi toga onda ima puno tih upozorenja, jer se treba sjetiti onda da ti ljudi nisu završili 3 razreda srednje škole samo zato što su si to možda željeli, jel? Nego vjerojatno zato što možda i nisu mogli pucati na nekakva malo složenija zanimanja zbog svojih mogućnosti učenja, spoznaja i slično, jel? To je to. Znači sad opisuju ovdje koji su to glavni, da tako kažem, dijelovi tih par točkica koje ovdje sad tu postoje, kak se meće da možete nositi preko ramena, to mi ne nosimo preko ramena i tak dalje. Onda sad tu dolaze, znači, oznake šta su tu pojedini ovi dijelovi, opet kak ide preko ramena i tak dalje. I sada je zapravo kaže sad je da se ovo što smo sad napravili, da smo ga tu zapravo korektirali. I sada zapravo sljedeća stvar koju ovdje kaže da treba napraviti, što sam ja već napravio, to je priključiti ovaj uređaj na sam naš takozvani test. Ja? I sad prva stvar koju će vas tražiti je da pita prema kojem standardu hoćete da se on zapravo testira. Ne? Standardi koji se ovdje pojavljuju je američki standard, znači to je ovaj najgornji redak. Znači u ovom tu slučaju ne, vi ovdje imate tu funkcijsku tablicu s kojom mijenjate po kojem standardu želite raditi mjerenje. Znači ova mjerenja koja se ovdje radi, mi ćemo se sad spojiti na ovaj standard o kojem sam govorio. Ovo je govori američki standard, American Association for Medical Instrumentation je ovaj AAMI. I ovo tu je standard koji je isto općeg karaktera, ali je on zapravo za medicinske sustave. Znači, sva ova testiranja koja ćemo mi na ovoj kanti ovdje sad napraviti, 5-6 tih mjerenja, se mogu raditi recimo i za onaj tamo ultrazvučni za ekstrakorporalnu lithotripsiju, gdje sigurno ima 10.000 šarafa, koji su negdje prisutni i načelno bi netko svaki od njih trebao dotaknuti. Ja neću ulaziti da se to uvijek baš tako radi i slično, ali sigurno u onom dijelu koji ima direktne veze s pacijentom, to naprave, tam možda na monitorima i slično, koja niko ne prčka s rukom, moguće da i ne naprave, ali ne smijemo sad reći šta ljudi rade ili šta ne.
Da su Amerikanci jedini posebni koji imaju poseban standard?
Ne. Stvar je u tome, dakle, da zapravo svaka zemlja ima svoje standarde, svoje norme. Međutim, potrebe tržišta danas su takve da ako hoćete biti globalni, da morate imati uređaj koji zadovoljava globalno tržište. Naravno da nekim Kinezima možda u prvom trenutku vrlo važno, da li zadovoljava to nekakvi standardi ili ne u Americi, jer vjerojatno onak neće u Ameriku prodavati. Znači ono što recimo Kinezi baš rade sada je to da pucaju na afričko tržište i one tamo latinsko-američke zemlje i slično, siromašnije. Zašto? Jer oni koliko god danas hvataju sa tehnologijom i slično svijet ili Ameriku ili Evropu, oni ipak još neke stvari uče. I isto kad gledate koja mora biti logika u toj zdravstvenoj skrbi i slično. Šta ćeš ti slati u recimo jednu Keniju, nekakvi MRI, kad tamo nema možda nijednog radiologa koji nije specijaliziran, jer nije to sad napraviš sliku. Možeš meni pokazati 100 slika sa MRI-a, ali mislim ja na njima, osim što možda mogu prepoznati neke organe i slično, ono drugo, ne znam kaj. Znači ne znam patologiju. A onda ne znam, u toj nekoj, zabrao sam je bila Kenija, Tanzanija, jedna od relativno velikih zemalja, 27 milijuna stanovnika u Keniji. Kad sam bio u nekoj komisiji u Svjetskoj zdravstvenoj organizaciji, to je bilo vezano uz karcinom, isto dijagnostika i tretman karcinoma. Šta je izašlo? Kaže čovjek tamo, kaže, ma da, mi sad pričamo tu o opremi, mi imamo u zemlji 3 ginekologa i 1 onkologa na 27 milijuna stanovnika. Kod njih je isključiva palijativa. Šta možeš napraviti da čovjeku omogućiš da što moguće lakše umre? Da li možeš nešto još spaliti prije toga? Sad je opet pitanje da mu radiš uslugu, da ga ostavljaš dulje na životu ili ne. Bilo je baš reći o tim ginekološkim karcinomima i slično. Žene dolaze već kad im se s opuštenjem grudi raspadaju. Nemaš ti sad tu puno nekih mogućnosti. Znači, svaka zemlja ima svoje standarde, međutim, ono što se događa je to da se prvenstveno recimo u Europskoj uniji, oni naprave da su kompatibilni, odnosno zapravo se ide na usvajanje po nacionalnim zemljama. Znači, kad dođe novi 601/1/ nešto, ono što će se dogoditi će biti to da će Hrvatska zapravo preuzeti tu normu i onda najčešće, čak na našoj razini ovdje u Hrvatskoj, onda kažu ok, prevodimo samo naslov, sve ostalo sve u originalu, načelno IEC piše na hrvatskom, na engleskom i na francuskom, na 2 jezika. Ne? I tako da recimo se većina valdogovornog područja, to je nekad izračunao, IEC ima središte u Švicarskoj. Tako da se plaćaju standardi u francima, recimo 601.1 je debel, mislim na 300-400 stranica i u tom smislu onda košta par stotina švicarskih franaka. To je to. No dobro. Kinezi, kažemo, mogu imati neke stvari malo labavije, jer oni idu na tržište gdje, kažem, tam pošalju neki dijagnostički uređaj za oslikavanje koji omogućuje čovjeku da nešto vidi, ali nema smisla puno detalja, ali jednostavno zdravstvo još nije doraslo. A tu u Europi, vidi se, sad Amerikanci su i Englezi počeli cijepiti, a Evropska unija je trebala još 3-4 dana da razmisli jel će dakle to kod njih proći ili ne. I često su to i samo administrativne zavrzlame, da tako kažem, ali u svakom slučaju, kažem, ide se na to da budu iste strane. Ima ih koji su loši, Indijci recimo. Mene su pozvali nešto baš da pričam o sigurnosti elektromedicinskih uređaja, to ispričam, velim kako su standardi važni, kako trebaju dobro napraviti da svi oni budu kompatibilni i slično. I za mene govori jedan stari Indijac, kaže, šta to? Mi imamo naše indijske standarde, dobro, ima ih milijardu i nešto. Dobro. Znači, to bi bila sad prva stvar koju smo napravili, to smo se odlučili, selektirali smo. Sad idemo vidjeti šta ćemo prvo testirati. Sad koliko se ja sjećam, prvo treba voltage testirati. Sad ono pitanje zašto je bitno s koje strane je šteka i slično. Sad tu kad pogledate imate live to neutral, live to earth, ok, a neutral to earth pola volta. Znači, zaštitno uzemljenje prema nuli razlika je pola volta, AC 50 Hz. To je ono, ne znam koliko se osjećate iz Keva, možda sam i tu spomenuo. Dakle, zatvara se strujni krug preko nule. A nula je uzemljena u trafostanici. A trafostanica može biti 5, 10, možda i više kilometara udaljena. U Zagrebu vjerojatno ne. I sad sva struja koja se vraća prolazi kroz taj kabel. I sad na tom kablu, kad se vrati, ne znam, ova vjerojatno dvorana ima, ne znam, ziheru od recimo 16 ampera i sad takvih zgrada na Feru ima 50, to je 50 puta, teorijski, 50 puta 16 ampera, tak mora biti žica projektirana. Kod neki presjek kad ide 15 puta, nešto se rekao, 50 puta po 16 ampera i tako dalje, a onda će biti neki pad, ne zna se koliko on smije biti, na neku udaljenost i slično. Dakle, to su stvari koje se na taj način doživljavaju, a to je ovih sad 500 milivolti, ako se sjećate, imali smo 400 i 500 milivolti, koje onda zapravo kazuju, kako se zove, o tome koliko je takav priključak na napajanje siguran i za kakav tip opreme se smije priključivati. Dakle, u ovom slučaju, recimo, ovo se ne bi smjelo priključivati u takvom dijelu, dakle, ovo napajanje koje sad gledamo, ovaj napon i otpor uzemljenja, ne bi smjeli ići, recimo, u operacijsku salu ili u intenzivnu njegu. To bi bilo to. Sad, nakon toga, mislim da ide neki otpor. Sad idemo vidjeti otpore. Sad imamo tu negdje nekakve otpore i sad prvo je tu otpor 0. Sljedeća sad faza je da se gleda zapravo koliki je otpor metalnih dijelova. I sad tu možemo pogledati da će se, znači mjeri se prema zaštitnom uzemljenju. I sad tu možemo vidjeti da nakon nekoliko, kako se zove, koraka, će se on tu na nekih, recimo, pola ohma stabilizirati. Zakaj se mijenjaju ove brojke? Kako se mijenja tako na ovom tu šarafu? Smetnje imam. Smetnje imam. Sad to promijenim, recimo, i ga metnem tu. I kao prvo gleda ima neko pražnje, nekog kapaciteta, jer sad zapravo ovo nije namijenjeno, dakle tu ima hrpa rasipnih kapaciteta koji se pojavljaju, ne? Evo. Viš, sad je recimo otišao ispod 6, ne? Zato kad sam malo skupilo ove žice, sad kad bi možda ih još malo skupio bi bilo još manje, ne? Ali ovog treba sad ne gledamo koja je apsolutna vrijednost koju bi on trebao postići. Sad će možda biti više zato što ga držim rukom. Pa je onda moj kapacitet još više, ne? Evo sad je možda isto koji i tamo prije, da i kad ga tu otpustim. Dobro, to je sad, mislim, to je sad opet ta stvar, bez obzira što sad mjerimo nešto što je zapravo bez veze, što je tu zapravo koliko jedna petlja skuplja nekakvih smetnji, ali to vam je ono, to imate kad mjerite EKG isto, ne? Znači ovo mi sad mjerimo i gledamo kroz promjenu nekakve impedancije, ne? Ali tih 50 Hz je uvijek tu prisutno, jer ovo nije oklopljeni kabel, ovo je obični kabel koji je žica i ima tu vjerojatno metar, možda čak i metar i 20. To je znači recimo taj primjer. I sad bi ja tak morao ići ne sa svakim šarafom, otići na primjer tu straga, tu ima isto tako nekako uzemljenje, sad tu možete isto doći pogledat, ne? Straga, kako se zove, ne? I ovaj tu šaraf na koji se zapravo može sad spajati taj uređaj da dođe do neko čvršće uzemljenje. Dakle, možemo ga negdje uzemljiti za nekakvu štangu, da tako kažem. Sad ne znam šta prikazuje.
0,40.
Da, znači tu je neka druga vrijednost. Ja možemo od ventilatora recimo uzeti šta tu je.
18, a ne spušta se jako. 1.1,5, 6.
Da, dobro, to je sad recimo tu, to su ovi od ventilatora, ti su vjerojatno na izolaciji ili nekako tu. Ovo je tu plastika i tako dalje, sad se nećemo analizirati zašto taj dio baš ide, ne ide i tako dalje, nego jednostavno da vidite da je to jedan od postupaka. Sad dolazimo do onih dijelova koje, ne znam da ćete ovo moći vidjeti, eventualno ako nas neko tamo prati slučajno, ne? Znači to su one sheme koje sam pokazao, one tri dijela, ne? Znači, sad zapravo se provjeravaju u biti ne, kolike se javljaju dakle nekakvi naponi između ovih pojedinih dakle dijelova koji su znači nula faza i samo zaštitno uzemljenje. I sad tu imate isto faze, ne da se ako se mjeri ohmski, onda se to gleda sa ohmetrom, onda treba biti što je mislim moguće veći kako se zove otpor između nekih stvari, recimo ne bi smjela uopće masa prema tu gore se vidjeti i tako. I sada kažemo performing, dakle 3 su testa koje se ovdje sad mogu vidjeti, vidite Protective Earth, dakle resistance, dakle gdje se gleda, to je sad za ovaj američki standard, ali isto je za evropske, ne? Ground wire resistance, earth leakage current, ground wire leakage current, touch or enclosure, ovdje, dakle to je usporedba između 601 i samog, da tako kažem, ovog američkog sustava, ne? Znači, oni kažu ground wire, a mi velimo protective earth. Ne, ovdje je earth leakage current, oni kažu naravno ground wire leakage current i tako dalje. I sad ako se tu priključe, recimo ne znam, negdje su mi amperi neki ostali, ali nema veze, možda ćemo doći kasnije na njih. Znači sad u principu kad bi ja tu priključio mikro kako se zove ampere, jel? Onda u principu se gleda opet dvije stvari. Znači, kad je uređaj ispravan, dakle kad ima zaštitni vod spojen i kad ga nema. To je ova stvar tu kad veli earth open ili closed. Ne? Znači sada u slučaju kad je earth open, nema zaštitnog uzemljenja, leakage current, ne, koji se u ovom slučaju se zove touch current, to je nekakvi touch current kad se dotaknete nekog od gornjih dijelova, će znači biti u tom slučaju 2 mikro ampere. Ne? Sad idemo ga otvoriti, to je closer, pardon, ispričavam se. Evo, sad kad je closano je on 0,3 mikroampere. Čovjek bi očekivao nekad se sad spojili zaštitno uzemljenje, da kad se zove to bude manje, međutim, evo, kao što se vidi, nije, da tako kažem, taj slučaj. Ne? to je to. I sad samo to je to, i što imamo tu. Touch current sad mjeri, znači kolika je struja kad se tu dotiče, kod toga sad nema veze sa tim imali ili nema spojeno zaštitno uzemljenje i standard, to sad više nemamo šta, da tako kažem, micati, jel? I sad, kako se zove, se to tako reda dalje. Znači, ovdje u principu, to sad isto je teško malo listati pa pogledati, a sad su u principu slike zapravo šta se na šta spaja, ne? Znači, tu se sad očito gleda kolika struja teče kroz mjerni uređaj ako se spojite na zaštitno uzemljenje, ne? Što on zapravo sad interno gleda. Treba vidjeti šta trebam pritisnuti da bih to dobio. Ovo je bilo ovdje. Aha, ne, to smo gledali ground leakage, to ono što smo sad gledali, ovih 2,8 odnosno 3 mikroampera. Chassis leakage, znači vodljivi dio, i sad se uključuje, dakle isključuje medical device između zemlje, dakle između kućišta i ovog ovdje. Samo kako on ide ovdje, šta je rekao. Aha, sad tu vodišta treba raditi. Dakle, ovak, ja bih sad predložio da vas više ne filim s time, jer u principu, dakle, vidjeli ste sad otprilike koliko je sad?
20 je to.
Sad moram još za drugu grupu isto tako malo prikazati slično. Znači, što se ovog tiče, kako se zove, sve moguće, dakle, kombinacije, kao što ste vidjeli, se sad tu mogu, kako se zove, isprobati i na temelju toga se onda ocjenjuje da li je taj uređaj, da tako kažem, zadovoljava norme ili ne. Znači, to je rutinsko provjeravanje, načelno gledano. Unutar 3 godine bi svi medicinski uređaji morali proći takvo testiranje. Ovi koji su kritični, ne znam, koji su intenzivno njezi i tako dalje, to je pol godine ili godinu. To bi otprilike bilo. Tako nešto. Dobro? Ok, pitanja? Dobro, ništa, ajde. Sretno sa ispitom i naučite barem nešto. Ok. I'm ready for you. Okay, so we will now first do something. I will now switch this device off. And anyway, as I said, this is the old version. There's much more typing in with the keyboard and so on. So this one is made as much simple as possible. This one is following the newest version of the standard. This one is actually old-fashioned because it's probably more than 20 years old. So this device is checking mainly some resistances, currents, primarily the leakage currents, and voltages between actually the parts, mainly where there should be no current or no voltage, or where the actual resistance should either be short or open, because that's the whole, so to say, idea. But we are not living in an ideal world, so we have to, so to say, check the devices in such a environment. So I'll just go to have some kind of a mind flow through the instructions for use, and like in all and every device, no matter whether it is a biomedical device, biomedical checking device, it means a measurement device, or some household device and so on, you always have some intended use. So the description of what is this device used for. Before that, in the introduction, they say what they are going to measure, what's possible to measure here. So actually you start with the line, because if you are testing this device by connecting it to the analyzer, which is then actually measuring some potential differences and so on and so on, if the mains voltage is not according to the standard, then you don't do the testing. So the reason for that might be that you have bad network, but since we are not in Africa or Caribbean or something like that, we have stable current the distribution, at least in big cities and so on. The other one, if let's say the voltage drops and it's not approximately 200, because it's like the 230 volts minus 10%, it's 107 volts, so it has to be above 207 volts. If let's say less, 180, then probably some isolation of the input transformer or something like that is not correct anymore, so you have some capacitive currents flowing through that and so on and so on. So that's why you have to measure the mains in such situation where you actually look at what is the voltage on the device, so no matter what is before that. Then you have the resistance of the ground wire. So he said we have line, that's where we are measuring 230 volts, and we are measuring that 230 volts against neutral or against protective earth. What's the difference? What's the difference between neutral and protective earth? Neutral is the line from some transformer that is actually, let's say, supplying current for whole block or something like that. So from there you have line 230 volts to take as much current you need for your appliances, but the current has to close. So the return current is going to the transformer. And in the transformer, the neutral is grounded. But here where you live, okay, in order to protect you, because on this path from the building where you live to the transformer, it may be several kilometers. So on this path, the voltage that rises because of all the collecting current might be high enough so that actually at the point where you touch a device or your house appliance, it might be higher than allowed by the standards, and that means that it's considered to be dangerous for your heart or for burns or whatsoever. Okay, so ground makes sure that you have real zero at the place where your building or your whatever you have is practically. So it's just beneath. So this ground, protective ground, is a metal network which is below this building, and it has good contact with earth where it's not dry, where it is wet, so that you have all the times a very, very low resistance. What's there in the transformer, you never know. Okay, fine, that's it. So then we have we said equipment current, so we can see how much this device needs to be operated. Ground wire leakage current, that means the one protective one, how much current is through that one. Leaking then chassis, that means when I touch one of these metallic parts that are contactable, how much current will flow towards the ground from there. Direct equipment leakage because from each of these parts that are metallic, there may be some current flowing out, so it may be also dangerous. And then we have point-to-point leakage and resistance, that means you take this one and another one, and then you try how much current is flowing from this one to, let's say, this metallic part, and so on and so on. So as you see already here, if you have to do that, hey, how many metallic parts you have, how many connectors, how many pins on the connector you have, so it takes quite a long time. Okay, so anyway, now the first thing is to switch the whole thing on, to switch this guy here on. And in order to do that, I will now take the plug and I will plug it in, okay? So what happens then is that it runs a kind of a self-test. While running a self-test, it promotes the device and it says which device that is. So we have already the first screen. But now I will do something else. Have a look what I'm doing. I'm taking the plug, okay, and I'm reversing it. Da. Pa, valjda možeš. Molim? Ha čuj, ako neće oprat prozore u mojoj sobi, onda nek ide. Okay, have a look. What's the message? The message is fault detected. What kind of a fault do you have? Just changed the direction, let's say, of the plug. This is the important thing, that the device wants to play, so to say, as simple as possible. Okay, so instead of having inside a switch that will change the protective earth and neutral, they ask you to make this change. Once you have done that, now it will be measuring correctly. So I will now go again to the self-testing, and then we will make both. Yeah, okay, so the first choice that we have to make is actually the choice of a standard that we will be, let's say, obeying. In this case, you have the American standard. AAMI is American Association of for Medical Instrumentation. You have the International Electrotechnical Commission 60601, or you have the other IEC standard, which is a standard for medical systems. That means, like you saw, like the small lithotripsy that is percutaneous, you will use this device. Sorry, you will use the first standard for that. If you use the other one that has the table, X-ray, and everything else, then most probably you have to use the other one. Okay. Fine. So we made already our selection here, and now it asks what kind of a test you want to do. So there are several tests that you can do. Firstly, let's say this is the voltage. So probably in this case, why it is beeping, okay, is that the voltage between neutral to earth is 0.5 volts. If you remember when I was talking about the allowed differences, we had like 40 millivolts for operating theaters, and then something else, 500 millivolts for the other case. So currently it's obviously wrong, we shouldn't be doing that. So I'll try to switch now to the current. Now let me see just another thing. No, it's okay. Okay. We go now to the current. Now we should see how much current this device is actually consuming. Obviously, it was not standard. know why there is no current flowing currently here. So it's obviously some mistake that I have made. But anyway, here you would see how much current it needs. So it's about 300 milliamperes that the device here is consuming. And the next thing that we can have a look is the different leakage currents. Okay, so in this case here, you can see that the ground leakage, that means the current that is flowing towards the protective ground will be about 0.3 microamps. Sorry. Okay. So that's when the neutral is closed, connected. Okay, that's okay. Very small current. What happens if we put to open? It's okay, because there is no change. Okay, it means it operates okay. And then let me see, what do we have here? Let me see with the polarity whether something changes. Yeah. So in case that we have the polarity, that's the polarity of the plug, in one direction it will be 1.2 or 1.3 microamps, in the other direction it will be actually less or more or less the same. So these are these tests, and then again, not to keep you too long, now we have the protective earth resistance. So what are we looking for here is actually the resistance of different points that we have on the housing. So these must be low, so it should be under 1 ohm. Okay, so what's the difference between this open and the closed neutral? If it's open, that means that protective earth is not connected. Okay, and if it's closed, that means that we have the connected earth. So this one obviously should be that high. He doesn't like something because it's high. With the previous group it was like 300 millions, so I don't know what I changed here. Okay, anyway, with this measurement you should actually go and touch every metal point on the equipment. So let's say here I'm on the back part, going down. You see here it's much better. Okay, now I mix it. So anyway, the idea of the whole testing is to go and to check every of the points where you have a contact, real contact, so to see actually the voltages, the leakage currents, and the resistances. So it's not a very funny job to do, but because of the safety of the patients, it's necessary to be done. And though it may be now, it may seem very boring to you, but in case that you are going to design any electromedical devices, you will have to take care of it. Okay, I won't keep you anymore. Is there any question? Okay, there is also a list of the standards there. It's just a list. You don't have to read them, because if I gave you the task to read it, then you would go to the exam in summertime, not now, because there is a lot of pages there, but you can just have a look which kind of equipment has to be tested. So, okay. So now I'll just switch this off, and then I'll need two of you to help me to take this down and also to see that I'm not forgetting something. So could you please put it here? Could you unplug me? This one, the first one, yeah. Yeah, okay, here. This one is extremely long. Okay. What do we need? I need my mobile phone. Then we need to switch this off. Okay. So let me see now whether we have everything. So now this is much more dangerous because we are going down, so it easily falls down. Okay. Okay. That's what I said. Okay, that's why all the medical devices are also tested against mechanical stress. Okay? Jenya.
I was wondering because you asked me like you asked me the other day in email.
Take the mask off. I don't understand.
Okay, like you asked me the other day why if I was okay because I wasn't going to class like the last one I think, but I wasn't. The last one was face to face on 7th of January or something like this, and I was, but there was nobody in the.
No. Actually,
I arrived late because
I know.
My internet is not working well in the dorm.
They'll have a look. I was here. When I came, it was like one person here. So I talked to him 10
Here?
minutes. That's right.
But here, face to face.
Yeah, yeah.
Ah, okay.
Yeah. But then you know, I said, okay, let's talk another 10 minutes. And in 10 minutes there was still nobody here. You know. Then I moved to my office.
Okay. Yeah.
And I was talking to him because it's Chrono. You know, he's I'm mentoring him. So we talked about his his work and so on. And then like already 20 minutes after the class should have started, Jaya called me that there are another 3 persons who came, and then he said oh, one has left. The one was Carlo, and then because I'm mentoring him, I called him on the phone, and I said, okay, if he is willing to return, then I will be talking to 4 people. That's fine, you know. But then he already left, and then I said, well.
I understand. I was just telling you, like, and the other day, like, I was sick, like, I couldn't.
Well, no, I got. My philosophy. Okay, we can close it from there. Let me see whether I have everything. So actually, my philosophy is that
you need help with this or anything? Okay.
My philosophy is that all of you students are coming here, and at least in Croatia, the education is for free. So if you don't come, if you miss something, that's your.
You're paid now. It is paid too. Yeah, I was telling you because you asked me, so just why. That's why. Like I know. I was going to ask you for the exam. When you, I read that what we have to do, and I read something that we have to do some, practical exercise, like in the last one, in the midterm.
Yeah, it will be. Have a look. It will
like with formulas and these things.
What you may expect strength duration curve, something with ultrasound where we had a few formulas like the calculation of the wavelength, if the frequency is this. I expect you, let's say, to know what would be the average velocity of ultrasound in the body, because that's something you have to have the